Hi Year 12. This video looks at our next topic, which is called further calculus. So we're going to be looking at inverse trig functions to start with. And you might be familiar with some of the formulas that I've got highlighted here in blue. And these are the ones that we're going to start using, and they are also on our HSC formula sheet. I'll just show you where they are. Okay, so if we jump into our HSC formula sheet, which you all should at this point be very familiar with, scrolling through that, we are not on the first page, we are down on the third page. We're down on the bottom of that third page, and what we're going to be looking at are these rules down here to start with. So you've probably been looking at them for ages. We just want to have a look at the form of them. So when we're looking at our inverse, sine, cosine, and tangent functions, we need to think back about when we worked on those in our Year 11 topic, inverse trig. And when we're using this rule, we need to just note that it's inverse sine of some f of x. And it's that f of x that we're using in our formulas, and we've got f dash of x in there. So that's to find dy dx of each of those. Okay, so jumping back into our Year 11 inverse trig function work, we looked at chapter 17, and we just have a look here. Our sine function, okay, is the black one, and our inverse sine function is the orange one here, which we've got down below here as well. What we need to remember is that our inverse functions exist only in a particular domain. So in this case, our inverse sine function existed in the domain minus pi over 2 up to pi over 2. Okay, if we have a look at our cosine curve, which is the black one here, and our inverse cosine curve was the interesting, strange looking one here, okay, that we've got there. And this one had a domain of 0 to pi. Okay, so we're only looking in that section along here, and we're still between 1 and minus 1 for our range. So just remembering those, and you'll need to look up those when we look at getting ready for the HSC a bit closer as well. And the inverse tan functions. The black lines up here are our tan, and the inverse tan is the orange one there, and it reflects around the line y equals x. So it's got the same domain that we're looking at as the sine function did. So just remembering those, because what we're doing is we're now going to be looking at integrating and differentiating those inverse trig functions. So we'll jump back into Year 12 now. So I'm going to be explicitly using our HSC formula sheets to differentiate. I think it's the best way. We don't need to learn something else, and we can just go straight from that sheet. So if we have a look at our first question down here, we want to differentiate the function y equals inverse sine of 3x. So looking at our formula sheet, this 3x is our f of x, and our f dash of x is going to be 3. So we just want to pop that straight into the formula. It's not difficult. So if we have a look up here, there's our formula. We've got f dash of x, which is our 3 on the top line down here. And on the bottom, we've got the square root of 1 minus f of x squared. So 1 minus 3x squared, which becomes 9x squared, and that's our answer. So that one's fairly straightforward. The next one here, we've got cosine inverse x on 2. So just noting that we've got our f of x being x over 2, so therefore our f dash of x is a half. Now when we pop that straight into the formula, we're going to get f dash of x with a negative in front of it over the square root of 1 minus f of x squared. It's going to look like that, but we are not going to be leaving a fraction like that on the bottom line, so I'm going to neaten that up. So the 2 that's up here, I've brought down to the bottom line. So it's over here, and I pop both the 1 and the x squared over a common denominator of 4, so I have this as my bottom line. Remembering then that I can take the square root of the top and the bottom. So if I take the square root of the bottom, I end up with 2. The 2 comes out the front, and they're going to cancel out. So in my next simplified form, the 2 over 2 has gone, and I'm left with the square root of 4 minus x squared on the bottom, and I've still got the negative 1 on the top, and that is how we want that to look. Okay, our next example wants us to find the derivative of e to inverse sine of x, and we're finding that with respect to x. So we're finding the derivative of inverse sine of x. We're going to what we're going to be doing is remembering that the derivative of an exponential is the derivative of the power up the top, and then the exponential goes back into place. So we want to find the derivative of this power first. So the derivative of sine is 1 over 1 minus x squared, remembering that's our f of x. So f dash of x is 1. So the derivative of the whole thing is our derivative of the sine. It comes out the front. And then we've got e, the sine inverse of x, back up the top. Okay. So we're going to be using our advanced knowledge now to look at equations and normals of curves as well. Our curves just happen to be inverse tan of x. So find the equation of the tangent to the curve, y is tan inverse of x, at the point 1 pi over 4. Okay, so that one's a fairly simple equation. We know that our gradient of the tangent is m, which is dy dx. So the derivative of inverse tan is 1 over 1 plus x squared, and I've just used the HSC formula sheet for that. And we're doing that at the point x equals 1. If I pop that in that formula, I end up with a half. So that's my gradient of the tangent to this curve. Using the gradient point formula, the equation of the tangent gets substituted into here, and it's at this point here with a gradient of a half. So y minus pi over 4 is a half, x minus 1, expanding by the half. And I've just, not wanting to leave it in a fraction format, I've just multiplied everything by 4, and I've got this one up here, and then I've gone to the general form and popped everything onto the left. So that would be my equation of the tangent. You need to work through the textbook with some questions, though I would like to show you the derivation of the formula for derivative of sine. I think would be a good thing to have a little look at. So I'm just going to talk you through the part in the textbook. So if we let y be inverse sine of x, then what that means is sine of y is equal to x. So we're just writing that back the other way. And we know that when we're looking at an inverse sine curve, we're in a particular value of between minus pi on 2 and pi over 2. So we need to take that into account in our question. So what we do know is then that we can actually work out what dx dy is. Okay, we used to dy dx, but that's just now differentiating x in terms of y. So dx dy would be cos of y, because the derivative of sine is cos. Now, because we're looking at cos being positive, we know that it's going to be positive in the first and fourth quadrant. Okay, so when we find out that when we want to find out what cos is, what we can do is just think of the formula that sine squared x plus cos squared x is equal to 1, rearranging that to get cos squared x is 1 minus sine squared of x, or in this case, cos squared y is 1 minus sine squared of y, and we're taking the square root of it. Instead of getting just the positive and the negative value, we're going to take the positive only because we're only in that first and fourth quadrant. So we've got this part here. Now, we know that because x is sine y, sine squared y can be written as x squared. So I can write my cos of y as the square root of 1 minus x squared. So therefore we know that dx dy, which we said is cos of y, is also going to be 1 minus x squared. So what we then can do, remembering that these are inverted, so therefore dy dx is going to be the reciprocal of dx dy. So I can rewrite that as 1 over the square root of 1 minus x squared. So that's where the formula comes from. The derivative of inverse of sine is 1 over 1 minus x squared. So we can do that for cos, we can do that for tan as well, using the same format.